Welcome to this presentation. My name is Mark Scythian. The date today is October 13th, 2025. So this presentation is going to focus on rifle comparative analysis, AR-15 versus other rifles. So we have 4 other rifles to compare against the AR-15 with respect to power and performance. So the first step is to convert the AR-15 specifications to their metric equivalents. So we've converted the muzzle velocity, the barrel length in meters. So then we have to calculate the firing time, which is the barrel length D divided into the muzzle velocity D over V. So this will yield the time it takes for the projectile to complete its firing. So we have 0.000519 seconds. Then we have our bullet mass, so we convert the grains to kilograms, 64.8 milligrams per grain. So we're using the 55 grain bullet mass for the AR-15, so we convert that to its milligrams value and then convert it to grams, and then from grams to kilograms, so we get this value here. Next we have to calculate the bullet acceleration, so we have delta V over T, the change in velocity, final velocity minus initial velocity divided by time, or the firing time. So we'll calculate an acceleration value of 1,521,387 meters per second squared. And then now we can calculate the force accelerating the bullet with respect to the AR-15 223 caliber, and that is a Newton's value of 5422.2 newtons. So we divide that value into 4.45 to get the pounds force accelerating the round, so that is 1218.5 pounds force. Next, we should focus on the ballistic power. So in this case, we have force times distance divided by time, so the force accelerating the round times the barrel distance. So we get our Newton meters value divided by the firing time. So 2223.14 Newton meters divided by the firing time, and that yields 1 Newton meter per second is 1 watt of power. So we calculate a ballistic power of 4.28 megawatts, so we could round that up to 4.3 megawatts. And then the kinetic energy is 1/2 times mass times velocity squared. So it's important to know that a high energy rifle supersedes a high powered rifle. So you always want to assess the power, actually the overall energy, not the power of a rifle. So in this case, it will be 1/2 mass times velocity squared, so that is the mass of the round times the velocity, muzzle velocity squared, and so we yield 1111 joules, and we know there's 1.36 joules to a foot-pound. I have that backwards, but it should be divided into 1.36. So we have kinetic energy of 817 foot-pounds for the AR-15, and then we have next the bullet impact pressure. So when the bullet reaches the target initially, without respect to the penetration depth, there will be an equal and opposite force, or the force accelerating the bullet is equal to the ricochet force initially on impact. So we're not concerned with the impact time, but just only the equal and opposite impact force. So that is equal to the force accelerating the bullet. So that would be 1218.5 pounds in the negative value, so negative 1218.5. So with certainty, we know that when the bullet makes its impact, it will deliver 1218.5 pounds of impact force. Then divided into the cross-sectional area of the round. So the caliber is the diameter of the round. So we can take pi r squared to calculate A. So A is the cross-sectional area of the bullet, and the caliber is equal to bullet diameter. So all we need to do is calculate pi r squared, so pi times the caliber diameter in inches divided by 2 for radius squared. So 0.223 caliber, and we'll get half of that to get the radius, and then we square the radius. We calculate a cross-sectional area of 0.039. So the force divided by the area is the pressure. So the AR-15 has a bullet impact pressure of 31,244 psi. So next we should calculate the smokeless gunpowder charge per round. And so when we're dealing with a long barrel or a rifle, there's about a 25 feet per second loss per barrel inch. And there isn't much loss from aerodynamic drag, but most of the loss is from the friction as the round is cut through the rifling lands in grooves. So there's about a 25 feet per second loss per barrel inch. And we know the potential energy is equal to the kinetic energy. So we can calculate the loss of 400 feet per second and then add this value to the rated velocity, 2590 feet per second. So we actually need an equivalent muzzle velocity of 2990 so that after the round overcomes the barrel friction cutting through the lands and grooves, it exits at 2590 feet per second. So the actual kinetic energy we need from the smokeless gunpowder is the value of 1/2 times the mass of the round times the actual rated FPS in meters per second. So we square that value and we calculate 1481 joules. And then the potential energy of smokeless gunpowder is on average 3504 joules per gram. So if we divide 1481 joules into 3504, we'll get the grams smokeless gunpowder that need to be loaded into the shell casing. And then we can multiply that value times 1,000 to get the milligrams, 423 milligrams. That's another typo there. We'll divide that into 64.8 milligrams per grain, so we get 6.53 grains. And so there's 6.53 grains per round smokeless gunpowder charge per round. And some may argue between 6.5 and 7.2. I've seen the specs, but this is the minimum requirement so that the most optimized output is incurred without excess or waste of smokeless gunpowder. So 6.53 grains is the smokeless gunpowder charge for the AR-15 223 using the 55 grain round in the 16-inch barrel at 2590 feet per second. So we have all the specs here. Next, we can focus on the gravity drop per 100 feet range. So all we have to do is divide the time it takes for the bullet to travel 100 feet to target. So 100 divided into 2590 feet per second. So we get this value in seconds. So we know the drop is 1/2 gravity times time squared. In this case on the vertical or y-axis. So we can take 1/2 times 9.81 times the time for bullet to reach 100-foot target, that value t squared. So when we evaluate this, we have a drop of 0.00731 meters times 3.28 feet, and then times 12 inches to a foot. And so we have a gravity drop over 100 per 100 feet of 0.3 inches with the AR-15 223 with a 55 grain round. So that's the methodology. We also have to include the drop, but we'll put all the rest of the specs in. So that's the methodology in evaluating any type of firearm for its power and performance. So in this case, we're dealing with M4 next, and the metric NATO 5.56 millimeters. So we know there's 25.4 millimeters to an inch, in this case in diameter. So the 5.56 is actually 0.219 inch caliber if we convert it to the US system of measure. And so the muzzle velocity, we calculate that that value, and then the bullet mass, 55 grains, is converted into its kilogram mass value. So that would be this value here. Then we have our barrel length converted to meters as well. .28 feet to a meter. So now we have 0.369 meter long barrel, the bullet mass, the bullet velocity in meters per second, and the caliber in inches caliber converted. So again, we use the same methodology. Calculate the firing time, the distance of the barrel in meters divided by the muzzle velocity in meters per second. So the firing time is established, we'll call that T. And an acceleration is velocity divided by time. So that's the muzzle velocity divided into the firing time. So we have our acceleration in meters per second squared. And then we calculate the force accelerating the bullet, so that would equal 88 newtons of force. And then of course 4.45 newtons force is equal to 1 pound of force. So we can divide this value here, get 18 pounds of force. Next is our kinetic energy. So that's 1/2 times the bullet mass times the muzzle velocity squared in kilograms mass and meters per second velocity. So we get 1490.6 joules, 1.36 joules to a foot-pound. So we divide this value out, and then we get 1096 foot-pounds kinetic energy. Next is the ballistic power, and this is only the power involved in the complete travel of the bullet through the barrel. So that's the force accelerating the bullet times D, the barrel length, F times D, then divided into T, the firing time. So we have to use the metric system, so Newton meters per second. 1 Newton meter per second is equal to 1 watt. So when we make the calculation, we calculate the ballistic power of approximately 7.4 megawatts, and that is only the power involved in accelerating the bullet through the barrel. But what takes precedent throughout the overall rating of a rifle is its kinetic energy. So next we want to know the impact pressure of the bullet. So we can take the bullet cross-sectional area, divide the diameter caliber. So 5.56 millimeters is also equal to 0.219 inches caliber diameter divided by 2 radius, then squared, then times pi. And so we're able to get the area, which is 0.0377 square inches. So we divide the force accelerating the bullet divided into the cross-sectional area of the bullet. And so upon impact, the M4 rifle will incur or exert 48,223 pounds per square inch of bullet impact pressure. Next, the Smokeless gunpowder charge. So we'll just carry on like we did with the last calculation. We have to find out how much we lose in feet per second muzzle velocity over a 14.5 inch barrel. So 14.5 times 25 plus 3,000 feet per second. So we actually need an equivalent of 3362.5 feet per second divided into 3.28. So we need 10, 25.15 meters per second. And that V squared, quantity squared, then times the mass, and then times 1/2. So we need an equivalent potential energy in the smokeless powder within the shell of 1873 joules. 3504 joules per gram is the potential energy of smokeless gunpowder. So we calculate 0.5345 grams times 1,000, so that's milligrams. 534.5 milligrams divided into 64.8 milligrams to a grain. So that is an 8.25 grain smokeless gunpowder charge. And so we'll just carry on, but one added item, the 12 gauge rifled slug bore, is of interest because we're using a purely rifled slug bore, so it's not using buckshot, but just only a 400 grain round. So very accessible, and we want to see how it compares to the M4 and the AR-15. So again, we can use the same methodology. So I'll run through this a lot faster here. So we have 12 gauge Mossberg 500. So first thing we do is we get the barrel length in meters, 0.61 meters. Then the muzzle velocity in meters per second. Then dividing the D into the V, we can get the firing time T. Then we can get the acceleration from those values. So we convert the 400 grains to kilograms. So 400 grain slug has an equivalent kilogram mass of 0.02592 kilograms. So then I missed one on the first AR-15, so I didn't get the drop in there, so correct that one. So 1/2 GT squared, so we know the round will drop over 100-foot distance. 0.2 inches, so we'll put that one in there. .28 inches, so actually let me go back there a little bit. So it drops 0.3 inches, the AR-15, and then the M4 drops 0.2 inches. Per 100 feet. Next, we can stay with the 12 gauge Mossberg 500 rifled slug bore at 400 grain round, 1560 feet per second. So again, it forces mass times acceleration. 400 grain round is 0.02592 kilograms times the acceleration, which is a lot less because we look at the V over the T, and it is a bigger round, right? But we want to see how much actual energy it's going to carry through the round compared to the M4 AR-15. So again, we have the ballistic power, which is a little more relevant to when you're building the barrels. If the ballistic power is within tolerance to the barrel structure, or I'll say the barrel integrity with respect to the ballistic power. So that is a key component. So that's more about the structures of the given weapon and how the maintenance holds up to it. So you're dealing with a little bit more power with the M4, but the energy is what takes precedent for how the bullet behaves upon the target. So we have a ballistic power of 4.6 megawatts with a 12 gauge Mossberg 500 carrying 400 grain round, 1560 feet per second, 24 inches. And so the kinetic energy is evaluated at 2155 foot-pounds. The bullet impact pressure is evaluated at 5177 psi. And then the actual smokeless gunpowder charge, that's over a 24-inch barrel, losing 25 feet per second per inch. So let's quantify quantify into 24.7 grains per shell on the 12 gauge Mossberg 500. And then the gravity drop, we can assume it's going to be a lot more. So 100 over 1560 feet per second. Quantify into T squared. So 100 divided into 1560 squared times the gravity, 9.81 times 0.5 is the gravity drop to delta dy. So it ends up 0.8 inches per 100 feet of travel is the gravity drop on the Slug gravity drop for the 12 gauge Mossberg 500 carrying the 400 grain round on average 1560 feet per second. So the last two will do the calculations, and I'll put the format track here. So now we have the 30-06, and we can imagine this is probably going to be the most energetic rifle across all five, but we have to prove that. So we have the muzzle velocity, the distance of the barrel, or the length of the barrel is the distance in this case. The rail is the barrel. So then the firing time established. Then the acceleration established. And then the mass of the round. So the force accelerating the 30-06 150 grain round is equal to 2,995 pounds of force. And so that translates to 13,328 newtons. So that force times the barrel length, 0.61 meters, Newton meters divided by the firing time. So we get a ballistic power of 2.2 megawatts. So that's being written on the left here. So the kinetic energy of the 30-06 round, we have 4065 joules. We divide that into 1.36, so this becomes 2989 foot-pounds. Caliber diameter, so that's the 0.3 inches divided by 2 for radius, then square times pi, so 0.0707 square inches. We divide the 2995 pounds per 0.0707 square inches. So 30-06 has a bullet impact pressure of 42,362 psi. And then the Smokeless gunpowder charge is .77 grains Smokeless gunpowder charge per 30-06 rifle shell / round, and then its gravity drop is 0.2 inches per 100 feet. And then lastly, we have the AR-10 rifle, which is the 308 caliber, 0.308 inches diameter caliber. And AR-10 is often missed, but there's many people who are avid AR-15 experts and users, and they don't really make too much of a fuss when they hear about the AR-15. So you can go up to the AR-10 instead and use a larger caliber, and you would assume it's going to be more powerful and more energetic than the AR-15. But we have to prove that, so we take the specs for the AR-10 rifle, 308 caliber, 2850 feet per second, 147 grain round, and a 16-inch barrel. So we use the same methodology to convert these values into the metric values for the scientific and engineering calculations. So then we can calculate the acceleration, firing time, distance, muzzle velocity, and the mass of the round in the standard metric values. So then we are able to calculate the force accelerating the AR-10 round, and that is 3,941 pounds of force, accelerating the AR-10 147 grain round, and then having a ballistic power of 15.2 megawatts. Then its kinetic energy, 2,644 foot-pounds. So we get the 308 caliber cross-sectional area, and then we divide the force accelerating the round into its cross-sectional area. So there's a 52,899 psi bullet impact pressure with the AR-10, and then second to lastly, we have to calculate the smokeless gunpowder charge per shell. And so this comes to 20.52 grains. And then the drop for the AR-10, drop for the AR-10, we could almost guesstimate it. It should be relatively close to probably the first two, but again, it is a slightly larger round, so yeah, we're going to have a drop of 0.24 inches per 100 feet. So if we order this from the most energetic rifle to the least energetic rifle, based on the engineering physics standard that the high energy rifle supersedes the high powered rifle, the 30-06 would be the most energetic rifle, followed by the AR-10, then the 12 gauge Mossberg 500 rifle slug bore, number 4 the M4 rifle, the M4 Carbine actually, and then the AR-15 is the least energetic. Now if we look at the power curve, the 12 gauge is slightly more powerful than the AR-15 because 4.6 megawatts versus 4.3, and then everything else is relatively in descending order, but the actual power accelerating the AR-10 308 round is higher than the 30-06, but the overall energy of the 30-06 is greater than the AR-10. So whenever you hear high power, that's more with respect to marketing, but the actual energy involved is what is going to translate to the performance. So without getting in an argument, we have the engineering physics analysis or analyses which prove that the most energetic rifle comparatively to these 4 other ones is the 30-06, followed by the AR-10, then the 12 gauge Mossberg with the 12 gauge Mossberg 500 with the rifled slug bore, followed by the M1 Carbine rifle, and then lastly the AR-15 compared to the other 4 is the least energetic rifle of the 5. So I'll put in the M4 Carbine. Thank you for watching this presentation and have a great day.